Hello and welcome, and this is the final video in our revision of Current Mirror, where I'll just conclude some final things about OTA, and then I'll just try to wrap up things by like final remarks of what I learned in this chapter. And then in the end, I'll just describe as of what I intend to do in the long run in this semester. And there, if you were just interested to just get the gist of this chapter, you can just skip this video. However, this is just for my revision. But in the end, like in the last 5 to 10 minutes, I'll just like summarize what I intend to do in the remaining portion of the semester. Okay, great. So last time we were just discussing where even on one thing I was getting a bit confused, and my confusion, to be honest, is still not that much clear. But what my doubt was that how does single-ended amplifier achieve common mode rejection? So, like we already saw that in a basic single-ended differential amplifier, when we are talking about the differential gain, we are for differential signal we are having a certain amount of amplification, and whereas for common mode signals the amplification is of some by some other margin. For example, if I were to write my gain for a single ended differential amplifier, it is of this order, whereas for the common mode gain, as we already have know and have already described, it is a kind of this form, right? Where this R is basically the resistance seen at tail. So this common mode gain is way lesser than the differential gain. So yes, we achieve some form of 60 RR, but the intuition behind that is not that clear to me. But yeah, that's the basic idea, that even a single input amplifier can have a common mode rejection, and that's why it is used to begin with. And when we said that there is always in for any general single-ended differential amplifier, there will always be certain amount of common mode to differential mode conversion, despite the fact that your circuit is perfectly matched, and that is the disadvantage that carries on forth in a five-stage OTA. Right. So here, if I try to write, so this is always not equal to zero for single-ended diaphragm. So this is the something that I have been able to conclude. And now that being said, now let us go to the next segment of this chapter, where we basically deal with the biasing of some standard three circuits, which are CS stage, stage, and CF stage. Now, before going back to the final circuit, let us try to arrive at the final bias circuit. So we know that the common stage amplifier looks like this, and we know that we feed the small signal to it something like this, and then we basically amplify. But now to have this amplifier working in saturation, we must bias its gate, right? And for that, we have various topologies which you already know. We have resistive biasing, and we have current source biasing, and so on and so forth. But right now we have just focused on one of the examples given in Razavi, where we are biasing this by a current mirror. So the idea is that you want to have some bias voltage VB over here, so that this circuit works in saturation. Again, to have the isolation between the incremental signal and the DC bias signal, we place a capacitor, right? Between the we place a capacitor between the input incremental signal and the bias signal. And this capacitor basically gets short at this incremental signal frequency, and here we try to generate V bias, and we can like arrive at that by a basic current mirror, right? And by this basic current mirror, we can arrive at the value of VB. And now, typically, what is desired is that, yes, this particular configuration will generate a VB which will bias this transistor. That is fine. But typically, the idea here is that the value of VB, the value of current that you use basically to generate this VB, it is typically desirable that you are able to generate this generate this VB by using, let us say, like ID current is flowing here. So you would want to generate this VB by using some lesser current over here, right? Like it should be like half or one fifth. So that means that W by L ratio of this guy will be more than W by L ratio of this guy. That's the basic idea. Okay, that is not that important point, but what is more important here is that will now this circuit be sufficient enough to bias this circuit without any further complication. To understand this, we must actually look at the small signal picture of the circuit. So the small signal picture will kind of look like this. And here we can see that there's that connected device. Here we have V in, and here we have yeah. So this is how the small signal picture looks like. And here we can see that for incremental signal or for basically high frequency signal, what is happening, this capacitor is getting shorted, and now this V in basically appears over here, right? And even if that was not the case, let us say that this node voltage only, it has sudden spikes or jumps, or like which basically translate to some high frequency distortion, that will directly come over here and that will just directly get amplified, right? So that is a kind of an issue. And there are other reasons also of doing this, but the big main idea here is that in the incremental model, what we want here is that the bias signal that we are generating, right? The bias signal which we are generating, VB, that VB should basically be blind to the incremental signal interaction because of this capacitor. So what we try to do here basically is to insert a big resistor over here. What happens by this is that whatever VB is being generated here for DC, this VB will come over here. But for incremental signals, this VN won't interact with this circuit, right? This VN will only be able to flow here. That's the basic idea, but I can't really justify why we are using a large R. So let us just come at this circuit step by step. And although at this point of time, I'm not very much clear as of why we are doing this, but I hope so that down the lane in time, I'll be able to appreciate this circuit better. So the basic idea was that you have this current mirror and you are generating some voltage VB. And now what you are doing here is that you are placing a large resistor over here. Okay, this R is large. And now you are basically attaching it with this capacitor circuit. This incremental circuit is over here. And now you have your basic CS amplifier. Okay. And now you have this R as large. So you can understand what this R is basically doing, that for incremental signal, this Vin won't be able to much seep in much here, and most of the signal will interact with this CS stage only, the incremental signal, whereas this PV, which is the bias voltage, will appear here without any much problem. And now to realize this resistor, since resistor practically consumes a lot of chip area, we try to realize this by a triode load, right? And to do so, what we do is that we have a transistor in triode region, which is we apply some bias voltage over here, and now we connect it this way. Now, how do you generate this bias voltage VG to keep this transistor in triode region? What can you do? Again, what we try to do is we try to also achieve this guy by using the current mirror only. And what we do is we do something like this, that the upper transistor here, it's sized such that it is generating this voltage VG, which is goes straight into this triode region transistor, which is basically functioning as a resistor. Okay, and now this transistor is basically generating your VB, right? So it's similar to that only, and this transistor now size such that it generates your required VB, it goes here, and then this circuit is like this. So it is same as this circuit only, but we are just trying to realize everything by means of transistor. Okay, and now as I see a stage, and here also like for some completeness, you can have this guy and this guy. Let us say it is diode connected whole time being. Okay, so this is your CS stage, right? And we implemented everything by using a transistor. Great, and since it's triode regime, so I can like keep this sign anywhere. But yeah, so this is our biased CH stage, And something that what I have not been able to fully understand here is the purpose of this guy. Okay. So I'll just also write it down here so that in future I can come back to this purpose of this guy. Next, this was the example given in Razavi as to how to bias a CA stage with a current mirror. Now, second example was for common gate stage, and here we know how a typical common gate stage looks like. Again, you have this bias, some bias voltage over here, and you have some resistor over here you have your V in, and here you have your V out, right? So that is how you basically have your CG stage. And the idea here is that you can generate your RS by RS, which basically you can generate your RS by a current mirror. And why is this a good idea? Is because you know that this circuit will you can you can basically like generate your VB by current mirror, which is something similar to what we have seen, and you can also generate RS by a current mirror, and we already have seen that we can have a triode load, and we can again bias it by a current mirror. So the philosophy is kind of similar to that. I have to reference the book for a bit so that I can recall things out, because the circuitry is does not look that much straightforward. So yeah. Okay, so now I can see how this circuit looks like, and now I am confident that yes, I can get this done. Okay, so the main idea is that we are trying to generate VB and also RS by means of the current mirror, and this how the circuit goes like. So first, let us draw the main amplifier stage. So this is our main amplifier stage, and now what we are trying to do is that let us also couple the input signal that has to be amplified. Okay, so let us place the input signal also that has to be amplified. Okay, and now here we have to create our triode load. Okay, or the load which from a resistor which has to act as resistance. It can also be a current source load, and it can be like triode load. It's all up to you. And this we are basically generating by means of a current mirror. And now if you now if you try to understand, like if I have to bias this transistor, there is one clever way how I can actually bias this. If you think about it, this kind of looks like a cascode structure in its own right, no? So what I can do here is that I can have this reference, I can have this I bias maybe, and I can have a transistor over here, I can have a transistor over here. And if you recall, as it is given in Razavi also, this structure, this structure, if you can recall, what was this structure? This structure is the structure of a high swing cascode, right? So this is the structure of a high swing cascode, and here we have to now think about the generation of V bias. But for time being, we have now basically biased this guy. We have basically put this guy have fixed the current through this guy, and by doing so, what you are able to achieve is a higher swing, right? Because this is a high swing cascode. So by ensuring the current flows like this, you have basically ensured a higher swing at this terminal. And you have to decide your VB accordingly, okay? So that you can bias your transistor that way. So this was the circuit given in Razavi, and the last example that has been laid out for us is by means of a source follower. And again, we already know how the source follower looks like. And here we have some V in, and again, you have a certain bias circuitry by which you can fix things out. And again, the thing which he has emphasized upon is not on biasing this guy, but on biasing the transistor at the bottom, because if you bias it well enough, you can ensure that the transistor is working as a current source, and then your work is pretty much simple. And the circuit which he has given out is pretty much straightforward as compared to the circuits that we saw in common source and common gate. And the circuit just looks like this. So this was the basic source follower stage, and he said that this voltage VDD, and he inserted a resistor here itself. And now what he did was to have this bias current and have this bias transistor, and here he connected it with this load transistor, and here you are observing your output. So this circuit is pretty much straightforward, and here he basically has tried to fix the node voltage by just placing a resistor between the supply rail and the gate. Again, over here, he has not really elaborated on VB generation at the gate, but we have already seen that how high swing cascode current mirror works, so we know what relative value of VB must be like. And this was just basically done as far as I can make out, so that the swing at this node can be improved. So this was all in this chapter, and if you just came for this, I think it's fine, and you can now stop watching this video. But now I just want to plan out more things for myself. So in this month, what we basically did so far, like today is 27th of January, and we have successfully revised Zawi chapter 1 to 5, and which are namely intro, then physics, basically related to MOS device, then single stage amplifiers, and then we also went through differential amplifiers, right? And then we went to current mirrors, right? So we also have gone through current mirrors. So five things have been done. What is left that is expected of me to what I am expected to know by end of this semester is basically frequency response, the chapter of noise, the chapter of feedback, the chapter of basically op amps, and specifically two-stage op amps, and basically stability and compensation. So these are the chapters that stand in my way. And like all the series in this videos, I was just making videos as of in my pursuit to cover what are the concepts that I learned in this chapter and log VLSI. And this is the things that I have covered so far. But I think why I was making this video series also was so that I could really revise things out for my upcoming internship tests and interviews if I'm able to clear. I'm only applying for Texas Instruments and a log profile, so let's see whether I'm able to convert that or not, because luck has not been pretty much on my side as things have been gone for me so far. So this was the main agenda, that why I was trying to make the series, so that I could really force myself to revise things and study things in greater depth. What I have covered, apart from Razavi's book and apart from Analog VLSI, which I covered last semester, is this the Shanti Pavan sir's Analog Electronics playlist, which has around 84 videos. That is something that I covered. Then Shambian sir's passive circuits I covered, and op-amp circuits. That is something that I have covered. And high frequency, high frequency analog circuit design, a high frequency circuit design by IIT Kanpur by Ashwin sir. That on YouTube, that is what I have covered. So what I'm planning to do maybe is that I don't think so. To be honest, making videos basically forces me to think about things more deeply than I would normally do in a revision when I'm not trying to record myself. So I'm trying to think this through. Like tomorrow is 27, and tomorrow probably my time will go in my FPGA assignment, and the time which I have left, in that time I'll try to revise passive circuits by Shambian sir, and if I'm able to complete the revision, I'll try to record it, or maybe I'll just do a live revision. Then also tomorrow that an Texas Instrument will come and give its like all layout, as of how it will kind of conduct its internship drive, and let's see whether I'm able to convert it or not. Also, after that only I can actually think about that how will I proceed with my remaining of the days. But some things that I have to do for sure is that I have to revise passive circuits tomorrow. After revising passive circuits, then I think I can really go for revision of Shanti Pawan sir's videos. And also I have registered for his course, so I'll just try to complete his assignment too also. So that is something that I try to do. So FPGA and Pasek is Shanti person I try to revise on his assignment. And another day also I can just dedicate to just revising Shanti sir's content. And after that, on 30 also, I can consider just revising Razavi maybe. And if I have time, maybe I can just go for revising Razavi chapter 6 after revising Shanti sir's content. And then I can just revise high frequency circuits. And other further planning, maybe I'll decide that maybe somewhere after I have seen I have seen TI what TI has laid out in plan for us, that when it will conduct its OA and interviews, and maybe I'll do further planning then. So yeah, so I think for time being, probably this is the last video of this month, or maybe for AVLSI at least. And if I am able to muster up that much of motivation and time, I'll try to revise passive circuits and try to record it and upload it just as a personal work for myself. I don't really think anyone has much to gain by watching this video, or maybe they have, I don't know. But if you are watching this, thanks for watching this video, and maybe I'll see you in next video in revision of passive circuits, and maybe in next 6 or 7 videos, maybe we'll be able to know whether we are able to get this guy or not. If not, good enough. But yeah, that's it for this video. And again, thanks for watching.